Hello everyone, Joshua back here, and welcome back to Universe Sandbox. Now, I played in the Universe Sandbox yesterday while I was waiting for Among Us to work. Now I'm back at it again. I am playing it for education today. Yes, I will be teaching guys all about the space and everything here. Let's first position lock the sun. So, let's see. So, one of the things that I noticed is that Mercury's orbit actually does shift around a bit. Like if you sit here and look, Mercury shifts. It just slowly shifts, going wider, smaller on each different side. Now if I continue pressing time on. Okay, I can go faster than 20 years a second. Okay, let's go a couple months a second. Maybe hours a second. So let's zoom in on Earth. The blue marble as its nickname. So this game has it wrong. The northern ice sheet is not like that. It looks to be May 5th. So it is. And now this is unrealistic. Okay, lesson one. Lesson one about the Earth and how ice sheets form. They form best over land. Now, for example, if you look at a map of the world's ice sheets during the huge ice age and everything, it will show you that most of the ice is concentrated in the northern hemisphere. Almost all of it is. There are a few outliers. There was, of course, Antarctica, but there was like an ice sheet that, because of how close a distance Antarctica is to South America, like right here during this in this pass, it was able to expand an ice sheet all the way up here. Another major exception was here, the Himalayas to the Tibetan Plateau. Then there was Tasmania. There was one on New Zealand. So it there was some elsewhere from the Northern Hemisphere, but almost everything in the whole theory of the Ice Age actually started here in the Alps Mountain. I'm pressing all the wrong keys. In the Alps, scientists and explorers have discovered glacial ice. Not like found glacial ice, not like ice. An example, down here in Africa, there's a mountain somewhere, well, volcano named Mount Kilimanjaro. Not ice like that, not from like mountain ice, but glacial ice. So the ice sheet expanded so far south, and because of the ice sheets, the ice age, sea levels were also a bit lower. Like, let's see, I don't know if we'll be able to get it, but if let's decrease Earth's average temperature to 0 degrees Celsius. Nope, I want 0. Okay, I'm not gonna get 0. So now, the Earth's average temperature is at freezing. So, at freezing, now this can't be accurate. See, look, what I was talking about. An ice sheet running through the Andes and whatnot. There was a huge one down here. And suspiciously, one place that remained ice-free was Siberia. Now, those of you who know where the Siberian climate and everything will know that it sounds odd. But there is actually, because of the less water hosted in Earth's atmosphere and everything, it made Siberia much drier than normal, so the ice sheet couldn't form up. I like how I think that's June, yeah, June. And then it's like summertime and some like winter in the northern hemisphere. Like these cities up here never see the sun. Also, these cloud currents. I do want to note that they are a bit wrong. So like up here, if you look in the top right corner, okay? I know what that's about. But if you look up here, you can see that there is clouds along the like equator moving correctly, but then up here is where it actually gets wrong. Those clouds up here are supposed to be moving this way. Like from the equator to believe it's 45. God, I can't remember. Or no, 60 north. They run this way, east to west, I think. That, that's actually just. Let's just screw around real quick. -10 Celsius. Almost all the land has ice on it. Now, of course, the temperature is going to try increasing because it's Earth. So let's go -50. So -50. Ice is starting to cover, but if we slowly. Oh, let's slow time down. If we continue to slowly drive the Earth colder and colder and colder, soon the water will start turning to ice. Well, it should. I think I think the surface water should turn ice like right now. I think it's -273 or absolute zero. The theoretical lowest temperature in the universe is when atoms stop moving. Wrong measurement. This one I can read. Atoms literally just stop moving. Now let's just give it average surface temperature 10. Yeah, so this is how the game breaks. This is how you break the game. Okay, new what the hell? What the I spawned Dimos? What the holy shit, Dimos caused. Alright, we're gonna be. Okay, so I'm going to teach us something very cool about our. Something very cool and unique. So, now the temperature's gonna slowly decrease until it reaches -273. Alright, there we go. So, it's because of the slow transitions. Now, the Earth is like this, so let's just bring it 10. Doesn't matter, it's just gonna decrease. So let's go forward until that -273. So we're going to warm the Earth up. Now, if we look at the surface, a surface map, there are some pockets of above absolute zero. But here's what we're gonna do. We're gonna be throwing let's see, a random small moon. We're going to launch it. So, I don't know how fast this thing's going, so we're going to decrease time quite a lot. What we're going to do is watch a surface map of this moon collide. And as it collides, energy is released. Complete and utter destruction is released. It's approaching closer. Okay, I would actually prefer the map to be over here, so hang on. Oh, do I have to keep this tab open? Okay. So we're gonna have to keep the tab open. So let's just go to 1 second per second. So this is real time. Okay? Target simulation speed. Now, this object is burning through the atmosphere, and it's starting to collide. So if you look on the map, and if you look on the surface here, there is a huge pocket of warmth. Up to 100,000 degrees Celsius. Now the average temperature is still minus 265 because most of the surface is covered in permanent ice at absolute zero. But if we speed the simulation up, the object disappears and now debris is released. Most of it will escape. Well, actually, most of it will get caught with Earth's gravity well, and then come back down to Earth, showering it completely. Some of it will escape, and then some of it will orbit. Now each collision brings the temperature up so much. Now, let's see. What if we were to put this Earth around a sun? So let's go get the sun real quick. I'm going to stealth it. We're going to put Earth 1 AU away from it. As close as you can get. We're literally just going to go into motion and just auto orbit. If I can find, yeah, auto orbit. So now Earth has an orbit. So we're gonna watch the graph, see what happens, because the sun, now the sun's energy will not hit the Earth yet. It will take about, well, it's already hit the Earth technically. So Earth's temperature will decrease, but now it will start its increase. Or that might be because the orbit, no, it will start its huge increase. If we look at the Earth, a huge crater has formed at the impact site. I believe, wow, we hit the Arabian Peninsula. We literally hit the Arabian Peninsula. But because of where we hit, it has... Hi, Wolf, we're doing education here. I literally just hit the Earth with a moon that orbits some planet, and I just added a sun in the simulation so the Earth orbits it. Let's actually add our moon to Earth so it has a more realistic orbit of it. Yeah, so this is another thing. The moon is so... Now, you may think, if you look at the night sky, especially during the supermoon, that the moon is massive. Let's actually do the view. Realistic. A realistic view. And I want to show you guys something. So, largest planet in the solar system. That's the sun, not the largest planet in the solar system. Sorry about that. Jupiter. Look at it. It doesn't even fit the distance. The distance is so unbelievably large from Earth to the moon that you can fit every single planet in between that distance. I don't know what the heck Planet 9 is. Is that like the fabled Planet 9 that we have no idea about? That we're trying to figure out or something? I don't know. Kepler 62. Ooh, Kepler system. Yeah, that might be fun. And let's get the largest moon in the solar system. Hang on, let me find Ganymede. So here's Ganymede next to the moon. Okay, that's fine. But let's continue in watching Earth warm up. Slowly but surely, Earth warm up. Can I get rid of this? Yes, there we go. So, the relation between Earth and its own moon, because of how the moon is formed, in its early stages of life, due to the solar system being brand new. Oh, apparently it's saying that that life has returned around this crater. Even though, let's check the temperature of the crater. It is 125 degrees Celsius. Oh wait, if it's 125 degrees Celsius, wait, did I place the sun correctly? Or am I just an idiot? Hold on. Where's view? Here we go. It's somewhere in here. Yeah, habitable. I think I put Earth. No, Earth is correctly placed, I believe. Alright, let's not mind that graph anymore. We know Earth is warming up. Quite literally. Global warming and everything due to human influence. Okay, so apparently places are starting to thaw out. So let's slow down time. Yeah, apparently life is returning. You know, you would think life would return right now. This is where the game is really broken. It's saying there's life. So let's follow the Indian subcontinent. It's literally still covered in permanent ice. But another thing, you can see how pronounced the Tibetan Plateau is. Arabia is just now sea. But you can really see how pronounced, like, the continents are. Like, you can kind of see China. The Philippines are, like, right here. But if you look at of course, there's the giant crater. Oh, things have calmed down in it. It's not 100 degrees anymore. It's on 19 degrees. I don't know what that was all about. But if you look at a surface map, you can... never mind. No, you can't. Elevation map. Here we go. So if we were to use how the elevation maps are for the entire... Like, what we'd use them for like, every single other planet out there. For example, like, Mars. We can... Like, we don't know what's sea level and what's not. Because there's no water. So, like, you can easily make out. So, what will happen with that is North America and Europe, along with all of Asia, except there is this one, like, dividing line. It's like the Willis, Wallachia, I don't even know. There's, like, this one line that divides Indonesia in half due to, like, Australian animals going up to the line, and then Afro-Eurasian animals going to the line but cannot cross the line themselves. But South America will get a new, like, a bit bigger landmass. And Antarctica, if you were to remove all the ice from Antarctica, it would actually be, wow, so the ice thickness is 0 kilometers despite the continents being covered in ice first. Sure, that makes sense. Yeah, ice thickness 5 kilometers. It'll be weird to see. It'll be insane to see how much more pronounced the see the composition. The composition of Earth. Yeah, the water level. All this just got moved around due to the collision from earlier. So if we switch to 2D and let's look at the surface temperature. Sea level temperature. No, surface temperature. So the highest temperature is in the middle of the crater because that is where the least amount of ice is, and that's where the deepest amount of water is. It's 19.5 degrees Celsius. It's still comfortable to sit in. As time goes on, the average temperature. Now the maximum temperature is for some reason is wanting to go down, but as time goes on, the ice on Earth will melt away. The ice that we created, of course. The entirety of all that ice will melt away. Now, that crater is still cooling. Oh, that crater is still cooling off from the collision. Or, no, it's because the seasons. We might have actually thrown off Earth's tilt a bit. Okay, let's see. Non-spherical gravity. Hold on. Let's see. Then gravity calculations assume all objects are perfectly spherical. In reality, spinning objects bulge slightly. So, technically, yeah, I'm gonna turn this on because the Earth is not a perfect sphere. We turn this off. Like, we get a really good look at where the equator is. Okay, so we turn it on. Apparently, this thing. That might be because of. Oh no, it's because the moon's effect of Earth's orbit. So, massive, large enough objects, they start to turn into spheres, but their rotation also drives how they're shaped. So, Earth is not a perfect sphere. A, because it has mountains, hills, and different continents, but B, it has its rotation bulges it at the equator. So you travel, I think you travel faster sitting on Earth at the equator than you do at the poles. It's like at the poles, like you barely have to move to rotate. But at the equator, you have to move so much just to rotate. Okay, we're turning the habitable zone off. So I will be speeding up the simulation a bit more so we can get the ice to melt faster. So okay. So some things are happening. The ice is finally melting. Another unique thing is the pure fact that Earth at some point in time in its history was something called a snowball. So due to surface and everything, now okay, let's continue to speed time up. And the average surface temperature is actually getting average surface temperature is getting warmer and warmer. And here we go. We have finally gotten oceans back. Now, there's still massive amounts of ice everywhere. That's due to okay, so now we can really see the effect of the collision. Because I started this simulation with just Earth, and we just put it around the sun. But let's continue. You can still define out the crater, the massive crater. And due to seasonal changes, you can see the surface temperature being affected. Now, unfortunately, the warming of the planet is starting to be all weird. So, due to some forces I cannot explain here, I believe we have finally gotten Earth to its equilibrium. Well, no, the temperature is fluctuating so much. There is some factor in play here. Because you look at the map, if you look up here, okay, what if we slowed the simulation down to about a month a second? It's still going by really fast, but the main thing is here, this temperature map is really on hand. So like it's gotten to like -4. So what if we put Earth's temperature? What if we pause it and just set 0? So due to its orbit and it not being perfect around the sun, so I just warmed it to 20 degrees. So its equilibrium point is in the minus of degrees. Okay, that makes a bit more sense now. So it will fluctuate around, like, in the -4 degree range. Now we can visit the new Arabian Sea. That is actually a really good name for it. So after the collision, there is actually it will be the Arabian Lake. It's not connected to any. So a lake is surrounded by complete land. Okay, a quick lesson. So let's open a new simulation so we can get just a bug standard Earth. Now, a lake and a sea are completely different. So for example, a sea is mostly made of salt water. And a lake is mostly made of fresh water. Now that separates the two. But that separates the two already. But a sea is also more likely connected to an ocean. So, for example, the biggest example I can get, Mediterranean Sea, the Black Sea. Now, here is where that definition gets blurred, the Caspian Sea. So, history lesson 2. Salt Lake City. Yeah, that is also true. And there's like another lake that's like water everywhere, not to drop a drink. I remember that from Civilization 6. But the Caspian Sea, biggest lake on Earth, but labeled a sea. So, a bit of history on that. Whenever this thing was discovered, it was thought to be the start of an endless ocean. So, one of the most documentations is from Greece, whenever Alexander the Great did the Alexander the Great things and conquered Persia, the Persian Empire. And this thing was discovered by them. And they thought it was part of the entire... Try to remember if it's Uranus or... What's Cronus' father's name? I think they're both the same. Hang on, you're not gonna hear music first. You're not gonna hear the game for a second. Oh, it's still Uranus. Okay, that makes some sense. So, to the Greeks, this was part of Uranus, which I believe Uranus is the name for like the entire sea. But we'll just say Panthalassa to make it easier, which translated from Greek means all sea. So this makes things a lot easier. Oh, come on. Ah, crap. I lost an earbud somewhere. I'll look for it after I'm done with the stream. So the Panthalassa. The Greeks thought it was part of it and named it accordingly to sea. Yes, that was also that, which turned out to be false. Now, they during like the Great European Age of Exploration, okay, let's go back into actual solar system so I can zoom in on Antarctica. They believed, like a lot of explorers believed, there was something down here, like something somewhere down there. They had no idea what they were looking for, because they had only discovered every continent but Antarctica. This was one of the I believe this was the last place to be discovered, or some other like random island in the middle of absolute nowhere. Probably somewhere. Well, no, because the Maui was like maybe down here. But a Russian explorer first discovered this continent, and the thing about this continent is that in the tech tree that they were at, of all the technologies during the colonial age, this thing is not really colonizable. It's just ice and penguins. That's all there really is here. So, okay, time to break the game real quick. There we go. That looks about right. Invertigo. Wait, I just had an idea. So what if, okay, What if we did inverted gravity on the sun? In negative luminosity? Whoa. Okay, so science lesson for luminosity. Luminosity, now I'm going to get the game's definition to help explain this. It's total energy released per second. It's pretty much how bright an object is. Surface temperature undefined. Can I get a graph of this? Okay, so negative luminosity. Let's see how well this plays out. Slow time way down. Okay, so negative luminosity. So apparently this thing... Yes, Antarctica is an archipelago covered in ice. Apparently negative luminosity changes the sun into this purple ball of, like, death. So let's see what effect it has on the planet. So, negative luminosity, you shouldn't be able to see these things. But, let's go to Earth. After 9 minutes, the light... So Earth should already be affected in such a huge negative way. All the sun is just gone. So it should decrease in temperature, and everything should go to absolute zero in the solar system, or close to it. Now, the sun may still host, like, any heat, but as far as we are concerned, like, as far as this game is concerned, it doesn't matter. Let's continue forward with time. Yeah, the Earth slowly is cooling down. So if you could look up here, you can see ice slowly spreading across the Earth as it enters the darkest ice age it's ever experienced in its life. So what we're going to do is, after everything goes dark, completely dark, and Earth is in, like, life as we know it. Now, life can still exist. I know, you may be saying that looking at the average temperature asking me, Jeshua, how can life still exist? At the very deepest parts of the ocean, where sunlight doesn't make a difference, life still exists down there. It will always exist because the animals down there, they feed off of just the water for energy. And that is it. It's like water... A negative temperature. Yeah, maybe. Like they feed off the water. At the ocean floor, they feed off the soil from the floor. If they're around a volcanic vent, they feed off the chemicals from the vents. They do not use photosynthesis at the very bottom of the ocean. So life can still exist on this beautiful planet of ours that we are unfortunately destroying. Is there a life probability index somewhere I can look at? Because that would be awesome. Effective temperature minus 273 Celsius. Yeah, maybe. Is there really no probability? Okay, here we go. Life likelihood. See, no matter, like, the temperature may be still dropping, but life probability, so completely speculative comparison to Earth's properties and necessary of life as we know it, based on Earth's simulator index plus rotation, water, and atmospheric mass. So, wow, the oceans are really starting to... What is happening? Like, can the oceans just freeze over already? There we go. See, the oceans take forever to, like, ice over because ice does not want to form on water at all. It literally barely can do it. That's why if you look at the ice sheets of the world, now of course the poles are, like, different. Like the North Pole, for example, has a tiny ice sheet compared to the South Pole. What happened? Okay, epilepsy warning, by the way. Just letting you know. Let me look at the sun while this thing is... Yeah, that's fine. Okay, so... Earth, minus 273. Let's turn the sun back on, okay? As cool as this looks, like... Whatever this is, let's turn this thing back on. Does your temperature change at all? Oh, it does, okay. Aren't you like the asteroid that's getting launched out? I mean, no, that's this thing. Oh wow, the Earth is actually warming pretty damn fast. Like, look how fast the Earth is warming back up. I don't think that would be true because when the Vikings discovered both Greenland and Iceland, they were the ones who named it. That's why it's named Greenland. Now, of course, in their own language, it was named Greenland, and then translate to English, it went to Greenland. So that is why it is not named Arctica. Now it is in the Arctic, but it's not named Arctica. So let's. So life on the surface was eradicated completely due to the most recent ice age that we purposely formed. Now, due to all the ice and everything, the Earth will only just barely warm up. Ever so slowly. It will take, I'm going to say, like a couple thousand years for the Earth to go back to normal due to the ice needing to start to fade away. So if we look at a map of the ice thickness. So let's. Nope, wrong thing. Oh, that's the wrong thing. But okay, and this works. Look at water depth. Okay, no, ice thickness. See, at the poles, the ice is getting more and more concentrated upon, but it's slowly going away in the center. Or hold on, this is weird. Okay, let's get rid of all these other graphs. That elevation's not going to change. So as you can see, the temperature's still just slightly increasing. But for some reason, ice is still mounting. Oh, it's because it's at the poles. The average surface temperature is slowly increasing from what I'm seeing from the screen. Like you can see the seasons change as well from this map. And because of how the way humans evolved was due to a necessity. And if you look at the aerial map of what the surface of Earth looks like, you can see, like if you look down here, you can see like Antarctica somewhat. Like with the ice expanding and decreasing, like the Antarctic shelf and everything. Now the ice should be slowly going away, and look, we're the average surface temperature. This is because Earth's orbit is not a perfect circle; it's a huge ellipse. It is an elliptical orbit. So the average temperature is corresponding to where it's at. So that's just gonna stay like that. What really makes a difference is now ice is starting to go away completely, and the ice sheets is starting to build up on the poles. I just leave my mouse here. Okay, for example, here the ice is waning away. It is slowly fading completely. And I chose a water spot because it's perfect. Now this thing is going by like a year a second, and it's continuing to fade away due to the sun's heat and everything. If we look at the aerial map, let's continue. Now it's glitching out sometimes because of how fast I had the simulation running. Now the maximum temperature is like 30, it's gone to 30 Celsius. Well, so if we raise the average temperature to 10 degrees Celsius, you can see the effects it will have. The ice sheets still go away. I don't even know what the average temperature of today's Earth is, but like the more you increase that temperature, the less ice sheets there are. But the average temperature, due to the ice sheets starting to fade away now, has been going up. Long Nap. I think the longest ice age was one of the earliest ice ages. I also just realized I read that message twice. Oh, we're back at the what the game says the ice sheets are like. Got it. So no matter how much we increase this, it's the game's depiction. But if you look at this just makes no sense. I think this is what happens. But the Ice Age, I would say like the main part of the Ice Age is done and through. The Ice Age is still there. Like the good chunk of the Earth's temp be bugging. Yep. Alright, so let's do not just planets. Hang on, let's do the solar system. So let's slow time way down. Let's do 1 second a second. Now we're going to sit here the entire time while this happens. You're about to see what? A supernova. Now, our sun cannot physically go supernova. It is unable to. It is not massive enough. Now we will sit here the entire 9 minutes it takes for there we go. So 1 second a second. Let's see. Let's go to Hawaii. I think this is Hawaii. Yep, this is Hawaii. Now it will take us 9 minutes to figure out that something happened. So at 3, well no. At 4:01, we will say science has discovered the sun has exploded and now we are fucked. So now Earth's title has changed because Jupiter is now the largest object in the solar system. Earth's title has changed to rogue object flying by Jupiter. Now if you want me to speed up the time, I can. Now we will sit here and watch the temperature, which is slowly decreasing for some reason. I don't understand why though, but that's fine. Because like as soon as the sun goes supernova, the temperature, oh no, maybe it's because extra particles and everything. Hey, that makes a bit more sense to me now. I just had to comprehend it out. So Earth's surface temperature is slowly rising. It's barely going up. I don't even think I landed near Hawaii. No, I did. So look, we haven't even detected this thing from Earth. Like, we haven't even seen that this has happened. And look how, and like, it's getting pretty big. Yeah, it's getting like, it's 10 suns the radius. Yeah, it's kind of... Actually, in the future, I believe it is proven true. Or not, it's just a concern. There is like a red dwarf that will reach the very outskirts of the Oort field of our solar system. And from the Oort cloud or Oort field, I don't remember what it's called, it's supposed to throw massive amounts of objects toward the inner solar system. So like if we get rid of the labels and trails, this is what we'll see from Earth. Hold on, let me change the view from enhanced to realistic. So this is the view from Earth. And we still haven't even detected this thing. We are sitting here thinking that the sun is completely there. Not realizing the temperature is slowly increasing. Not only that, that this thing is coming, that we are fucked. Let me get this to the side real quick. So let remove this. Remove this aerial view, and doesn't matter. Liquid water depth, elevation. Elevation doesn't matter. Actually, hang on. That's why I do want to. There we go. Surface temperature. Let's do an aerial view. So we have these three graphs to look at. What in the world? Do I have to do this? What? Okay, it doesn't matter. Okay, it doesn't matter. So you're gonna marvel at this. So we're going 1 second by second, and Earth's temperature has already been raised 1/10 of a degree. Average temperature too. So if you look at the graph, like these numbers don't seem to be changing, but all in here, the color spectrum is like everything should be going toward this yellow color spectrum. Reason being, once this thing starts touching, like once the mass amounts of X-rays and everything start touching the Earth, oh, that is nice. So if you look at the stars in the background, or wait, no, that's because they're, nope, those aren't stars. Those are asteroids and stuff like that. Never mind. I just realized my logo is blocking part of the thing. You should have let me know that, because that's not supposed to be there. We're not playing Among Us. That's only there for Among Us. I completely forgot about it. I somewhat do. So, we are 3 minutes away from realizing the sun has exploded into supernova, and let's look for a tiny little. Let's. Mercury is right here. Okay, let's get a Let's actually do this real quick. Let's go toward Mercury. Mercury is right here. That's how big this thing's gotten. The sun, if I were to have the sun and everything, here's the size of the sun compared to it. That's the size of the sun. So, it's really a significant difference size-wise. Now, this thing is 29 suns. It's traveling at 0.069 light speed. It should actually be traveling at 1 light speed, but apparently that doesn't match over. Let's go back to Now we can still have these names in the sky because we'll slowly watch. So Saturn's over there. Jupiter is. There you go. I fixed it. Okay, let's speed up time a bit. Because this is going to take forever. So we're at 16 seconds per second. Now we have figured out, the scientists on Earth have figured out, this thing just went supernova. Our own sun just went supernova. And now, everyone's in a panic. Because we just saw the tiny supernova, and scientists are already going to predict that this thing's much larger, which it is. And this thing's going to slowly expand. And if you look at the surface map, the aerial view, you will see the ice sheets just vaporize away. How far away is this thing still? I mean, tiny little Mercury just got swallowed up, isn't it? Yeah. I don't realize I'm exploding. It's like, they don't. Oh, yeah, there we go. That's getting some head. Now, this thing is just beautiful. But, unfortunately, the world is doomed. Now, part of the outskirts of the solar system will actually be saved from this disaster. Because they'll fly away just in time to not receive the brunt of everything. But, as you can see, surface temperature is starting to actually increase. If you look at the surface map. Here we go. Now let's zoom out to it. And now, there you go. Venus is inside of it. And now, Earth. So, from supernova, there's so much gamma, X-rays, there's so much, like, radiation. It's going to vaporize the magnetosphere. Let's actually get that up real quick. I believe it's in surface. Oh, because... Okay, so I just realized. So, because of how... in the sun's new red giant phase. Actually, I do not know. Well, the red giant phase of the sun, let's first watch as Earth just gets hit with so much radiation. Just look at the surface map. Now, if you see where all the energy's been concentrated, yeah, look. Now, you can start to see lava form from where it's showing, like where the Earth side is facing, and it's just getting vaporized away. It's heating up so fast. And it's just vaporizing away. Now there's still ice on it because of reasons. Probably because this is happening so fast, these things do not have any time to melt. And the fact that it's like concentrated in like 18,000 degrees. Which, for those that don't use it, 35,000 degrees Fahrenheit. It's a bit bright. Up. The game. Oh, the game does that. There's still a bit. Oh. Hey, Earth is vaporizing away. Bam. How did Venus last longer than Earth? Venus is much closer. There we go. As this thing grows, I think certain places shall survive. Like, I think Jupiter. Nope, Jupiter's screwed. Okay. Too much of a Chad. I think the supernova will just continue increasing in size forever. Okay, if you look at the radius, it transitions into Milky Way radius measurements. Oh no, it just disappeared. Okay. Yeah, those objects are just gonna fly away forever. Okay, so let's. So do you in the sun's red giant phase, do I think Mars will become the new Earth? Well, actually, that's a really good question. So let's first. Okay. Nope, it didn't work. And lock this. So, let's go. I don't know the size of the sun when it reaches red giant. So let's first get that. 256 times its current size. Okay, so that will swell up. So 256 sun. Now, problem here is that the sun will not be as bright. It'll be more of a reddish tint because the sun, as it actually, let's just go back to its normal like 5K and let's see if we can mess with the luminosity. Oh no, that is not what we want. Okay, hold on. Okay, so that stays the same. Gotcha. Can't. Alright, restart the system real quick. Hang on, redo. So, now the game does not simulate the actual like color and everything of the sun. So let's increase the radius. Lock that. That will go to 1. Lock it again. 250. No, that would be way too big. So 256 sun. Do I think that Mars here will be the new Earth? Now, if we are keeping the sun's habitable zone, if we do habitable, okay, that is a problem. Interesting. Gotcha. So, let's try this again, shall we? Let's go 200 suns. No, we need to actually do the correct measurement, though. So, let's think here. Okay, so, before the sun kind of... Okay, so... Gotcha. We can't really simulate that. So, I have an idea. Let's get... Idea? A. Delete sun. B. Turn on grid so we can get 0, 0. Which is right here. And C. Go into... going to add stars, and let's get already. Okay, maybe not that massive, as not that big a star. Nope, Rigel's a blue giant. Arcturus, that's an orange giant. That one's a red intermediate supergiant. We just need. Is there a future sun in here somewhere? North Star, no. UI Scooty, yeah, no thank you. UI Scooty, UI Canis Material, no. Nope, definitely not Proxima Centauri. Okay, so let's just add the sun back real quick. Alright, hold on. Let's see. Is there actually anything within the... There's a workshop. Yeah, hold on, let me... So I will have to leave the game real quick. So I just want to... Because your question actually does make me a bit curious. Will Mars become... Now, the new Earth. Now, in my opinion, before we even start experimenting with all that, I believe no. I believe that the sun will be far too bright for life to exist on Mars anymore. I believe that we'll be deep in our solar system. Europa, Titan, the moons of the gas giants. I believe we'll be way out there. So, let's see. Where do I go for user objects? Actually, where do I go for the user objects? Okay, so is it in here? Actually, where do I go? That would be a good idea. Start all simulations pause so I can explain them a bit. Okay, so. Okay. As this is space probes and asteroids. I believe that solar system go boom. Alright, so, here we go. I actually want to explain, I'm going to teach us. Alright, so I don't like how it's paused, hang on. Nope, nope. There you go. Whoops, wrong click. Alright, so, that's where I find it. So, this guy's measurement is completely wrong. But let's continue. This guy's measurement is wrong. This is not the correct measurement. But, in this event, now the sun is only 3,000 degrees. Now, with the sun like that, Mars is already on, like, complete lava. Okay, so this is wrong. Let's go get. Let's go get So let's see. Let's actually. I'm gonna explain to something that I mentioned yesterday, and I did get a DM on Discord about it, and I did say that I was gonna teach it today. The Roche limit, or Roche limit. So I barely understand this as myself, but so take these two. Let's positionally lock Earth so these two don't accidentally collide. I purposely have them orbiting. Now you're classified as the moon orbiting Earth, yes. So the Roche limit and Roche limit has this huge fancy equation that I barely can wrap my head around, and basically it says that this moon will be ripped to shreds. And it will, because the gravitational pull of the Earth and the moon collide with each other. They resist, and that forces one of the objects, especially if it's a smaller size. A smaller sized object has a more likely chance to be the one ripped to shreds. Now, density, mass, radius, all three of those factor into it. But because of Earth being, oh yeah, don't mind the beautifulness of these collisions. Now the moon has been, ooh, oh that's because the fragments large enough are colliding with the moon. Exactly. Now Earth got its ring back. Earth did at one point in time have a ring. It was whenever a Mars-sized object collided with Earth. Now, when I say collided, it actually grazed past Earth, like it grazed into Earth, knocking Earth, like tilting it a bit, which gives us our seasons, and also wrapped Earth in a huge ring, which formed our very own moon. Which is why the moon, like Earth technically should not have a moon. Mars is the closest planet that should have a moon because its proximity to the asteroid belt. Jupiter, due to its mass, and Saturn, like all the other, like gas, like the gas and ice giants should have their moons because of their mass. Now, let's say we. Let's say we did this. I think for the equation to continue working, the moon just needs to be like real close, but that's pushing it. Okay, so there was a community workshop about this, right? Okay, it has to download. Hey, this may not be 100% accurately made, but it works. So this is red giant sun. Okay, so this is about 5 billion years from now during its red giant phase. Actually, Mars does have 2 moons. That's due to. Okay, let's first see if this thing even runs. It barely runs because they added all the moons and you made it barely running, dude. Alright, so To answer your question on do I think Mars will be habitable? Oh my god. I did not think that this person would do that. Okay, so this might be another reason. Between now and this time, one of Mars's moons, Phobos, will actually get too close to the planet, and it will be ripped to shreds. Or collide. One of those two events will happen. This one went on the collision route. Not the collision, with the rip to shreds route. Maybe even a collision, because look, you see some particles like flying away? Or are those orbiting? I can't tell. Does Earth still have its moon? It's a good question. No, perfect. The thing is, it's pretty damn close. Let's see. So, 5 billion years from now, like, look at the orb, look at where you need to be. Now, I talked about Europa and Titan. Now, Titan, oh god. Let me get rid of the trails. Where's Titan? Why is Saturn looking weird? Does this actually happen because of... There's Titan. So Titan should still be habitable for humans. Unless... Yeah, let's see. Oh no, we can't really do that. Okay, so we can't fast forward like months and months and months. So Titan, I believe, should still be at least some sort of habitability due to the density of its atmosphere. And if we were smart, we'd probably kind of like pump more greenhouse gases into the atmosphere to preserve the atmosphere from the sun's UV radiation. But if we were... But 5 billion years from now, we should be in other systems. For example, let's go to the Alpha Centauri triple system. Now, it says it here, closest system to the sun. Binary stars, and then Alpha Centauri A and Alpha Centauri B. And it talks about... You need to zoom out to see Proxima Centauri. Okay, there's Proxima Centauri. So Alpha Centauri B. So the base center here of the binary system is a mathematical point. Okay, here we go. This is Alpha Centauri BC. But let's talk about the base center. So, the Berry center. This triple system. Now, this thing also orbits it, but this star orbiting Proxima B. Oh, they're in their own system. So, at Berry Center carries... Oh, wow. So, yeah, these things take forever to orbit each other, too. So, the Berry Center is where the two masses are combined, and that's where they orbit around. That's why the orbit looks like this. If you go into O... So since Alpha Centauri A is more massive than Alpha Centauri B, it dominates. In this game it dominates. Instead of both of them orbiting this. Because the barycenter does move around. It's a mathematical point, and it has this mass. So we should not do anything to it. Now, Proxima Centauri is a lovely little exoplanet to us. Apparently, according to this, it's a binary system. Imagine there was a star that had stars orbiting with the same number and size of our solar system. That would be insane. But the reason why that doesn't happen is because the stars won't interfere with that entire system due to the gravitational well. So, apparently, these two things are in a binary system too. According to the somehow 0.13 sun. Let's make this into Earth mass. So this thing is barely bigger than Jupiter. So if I grab Jupiter right now, hang on. If I grab Jupiter, like this thing is barely bigger than it. And if I place Jupiter here, it's gonna get ripped to shreds, and that's something that we're not doing yet. There's still a teaching moment with Proxima Centauri. Proxima Centauri is the closest star to our solar system, being like 4.2 something light years away, I believe. So apparently the orbital planet, like these two are in a binary system. Now that's probably due to the low mass of the star in comparison to here. Now, this has more mass than the Earth, and if we look at the composition, everything is solid except for hydrogen, which is a gas. So the water is frozen due to the surface temperature. Now if we do this view habitable, it is somewhat within the habitable zone, but due to mostly a lack of an atmosphere, it does not. No, Proxima Centauri actually orbit this system in the simulation? I don't know. It should. But the Proxima Centauri does not affect the barycenter that much. It's mostly due to A and B. Now if we look here at both of these, okay, let's get rid of that. It has a planet well within its habitable zone, and it's about the same size. It has similar size to the sun, well, mass to the sun, but if we look at sun, kinda light second. Oh, it's 2 light seconds across. What about Milky Way? Yeah, kind of expected that. Earth, no, let's get back to Jupiter. It's actually just auto it. But this also, now let's see, let's actually look through and see what the reasoning is. Okay, I do need to use the bathroom soon, so I will go into the solar system and have awesomeness occur. I believe it's under composition. Lack of magnetosphere. So harmful UV radiation's always bombarding it, so life is not possible. Well, it says here, life actually could be very well possible because it looks like the waters here are liquid. The game is saying solid/liquid level, but the gas is what's missing for an actual water cycle. So life is actually theoretically possible due to the water. There. Now if we go here, let's go back to Proxima B. It's only solid, but here's the main thing. Due to the size of the planet, the fact that it also does not have a magnetosphere. If we put the same magnetosphere for this as there is on Earth, problem also being magnetic axis is that, like, what in the world is this? Oh, because what? Huh? Okay. So even with the magnetosphere, it doesn't matter. So we add magnetosphere to Alpha Centauri BC. We should also see like a life likelihood increase. So I'm only doing Earth's magnetosphere too. I think it's doing it toward the very center. Now, the unfortunate thing about a magnetosphere on either of these planets is that, especially Alpha Centauri B, whenever it's like this, A and whenever C is in BC is in between A and B, its magnetosphere will be smashed, and it will slowly be ripped away due to it. Actually, it will just grow and shrink. Now, Earth's similarity index is increasing and decreasing, probably due to the seasonal changes. But the problem having two stars is plant life. See, the way plants work, and this is still hugely theoretical. Now we will go to the Trappist-1 system, the most unique system in the entire universe we've found so far, other than, of course, the solar system because of life. So if we make this one gauss, like, can it even hold that? Okay, what about 100? About 1,000? How much of a magnetosphere can you add to this thing? What about 1 Tesla? And I think this is literally just impossible. I don't think this planet can sustain a magnetosphere this size. There we go. Alright, so, let's see here. Yeah, that entire thing that we just did. It's just so, like, if we look at the temperature, it should actually somewhat stabilize, but it's just get rid of it. Now, I do want to test some out. Before I go use the bathroom, Jupiter, does it have a magnetosphere? It probably should due to the density of its core and everything. It does. 11 suns big. That's what happened. Okay. It's actually 0.622 Tesla. Now, magnetic pole is 10 degrees opposite, minus 10. But there's 0% life likelihood due to gas giant. What about the sun? Can we actually... It literally doesn't have a magnetosphere. I mean, if it did, it'd be like 10 Tesla, though, wouldn't it? I really think it matters. I got still somewhat similar to Earth. What if we made this... We'll just continue making this thing super old. So this game is kind of bugged out like that too. So it shouldn't be, the sun shouldn't be able to get this old. Can I just go to this E number and just... No, okay, got it. See, this is... I don't get this sometimes. Hey, let's... Here, watch a... I believe this is real time. Nope, this is not real time. Okay. Well, I go to the bathroom. Let me simulate this out 1 second. We'll be... And I will be showing... Hey. As this collision takes place, I'll be going to the bathroom. Enjoy watching this collision. I'll be right back. Give me in real time too. Have fun. Let's go to 5 seconds a second. Let's speed this up. Let's actually go to what the simulation wants us to do. Just 12 seconds a second. 12 times speed. Now, this collision will do several things. A, Earth is dead. Like, I believe there should be... Well, Earth got bigger. It got more mass. It got more compact now. What I find under... Yeah, Earth's life likelihood is vaporizing away. You need a simulated index. So, as the Earth... Well, as the temperature starts to spread, try to disperse evenly... throughout the Earth... Oh, it's because I'm hitting the top. This thing will be continue to grow, which is literally just a field of plasma. It will continue to grow and engulf the entire Earth. Now, with this collision, oh no, it stops. Okay. A magnitude. Now, with the dinosaurs, a magnitude 11 earthquake happened when the asteroid of the dinosaurs that killed. Also, everything is a gas, so Earth's core has now superheated again. It's now gone back to even more liquidation. Wait, why? Oh, what? Let's see, is this better? Can you hear me now? Okay, so I don't know what happened there. Got it. So Trappist-1F. This one actually does have water. It says solid, but it looks liquid on here. Is there anywhere to like not show an atmosphere, but like not show an atmosphere? Well, atmospheric mass is decreasing, but it's so slow that it doesn't really matter. No, I can't. Got it. Because it would be on the atmosphere. It's mostly made of. It has 1% water, more water than Earth does. It has like a good amount of iron and silicate, but Magnetosphere doesn't have one. We gave one that Earth has. I think that would be a lot better. For life likelihood, should go up now. No, the max. No, that actually clears out some land. Or something. Something happened here. I don't know what happened, so let's just remove it. Man, I play this game some a good amount of times, and I don't even know what the hell happened here. Probably because the ice. Okay, that's a lot of kilos lost. Hey, and then yeah, and then the furthest one out is Trappist-1G. Hey, slow down, you happy bastards. Which, if we look at composition, everything's solid, but of course hydrogen is a gas, no magnetosphere. Let's give it. So one gauze. I don't know what the difference between gauze and like I don't know what gauze is reference of. So let's give it Earth's magnetosphere. Now life likelihood is non-existent here. I'm trying to see if I can make it happen. No, okay. So the reason why a magnetosphere is shaped like this is because the stellar winds from any star is actually pushing against the magnetosphere. And so what happens is it gets elongated to where it's oh, we can change this up. Hell yeah. Clouds. Duh, blood red. City lights. Show. Apparently life can show here. Okay, snow. Blue. We all know snow is blue. Same thing with ice, but ice is a bit lighter blue. And water, we know water is green. See, look. Look how hideous this is. I'm actually curious. Here's the main star, Trappist-1. Now, the unfortunate thing about this system is, yes, these planets may lie within the habitable zone, but the problem with this is, this thing is barely bigger than Jupiter. It's tightly packed in, but this luminosity and then these orbital periods, like this planet takes, this planet takes 1 day, a single Earth day to rotate. Well, a day and a half. So, 36 hours, and that's roughly 36 hours. And so these planets will be, I just know, planetary system. What? Oh, is it talking about, like, the mass? So I do have an idea of what we can do with this planet, you know? Let's turn this thing into a star. Okay, since I use this thing quite often, we're gonna do this. This way, now I don't have to stupidly go into it. Let's turn this thing into a star. Hydrogen, let's make it 1 Earth per particle. Okay, let's slow down simulation. I didn't realize this thing's actually far from its star. Actually, let's create a star. Let's just create a star from scratch. We will start completely from scratch. Now, we will have, when I say completely from scratch, we're kind of cheating a bit. We're going to get a random asteroid. Just put it here. We can get like 1,000 kilos or something. I don't know. What's the mass of this thing in kilos? Okay, so we can add a bit more than 1,000 kilos. Let's add 10e plus 5. Okay, so these things are traveling too fast. So let's make it 1 kilometer a second. Let's see if that works. No, it doesn't. Okay. So let's delete you. And I got rid of the asteroid that we're using. Okay, so let's get maybe a random small moon. We'll start with the small moon. Now, what we'll do with this moon is we'll change the composition and make it all of hydrogen. And now we will decrease the mass. We'll decrease the radius mostly. There you go. Let's start with the thing 200 kilometers. Whoa. Okay, here we go. Now let's get graph and graph and graph. This way we don't need to look at it. So as we add stuff, just trying to get rid of this stuff. I will force you to grow. Okay, so let's... Okay, that's a bit too much growth. Okay. Just add more of this stuff. There you go. This should be interesting. This is gonna create a black hole, though. Yep. It got two... Yeah, so you see like the mass just like exploded. And then... Yeah, massive... Okay, let's restart. Okay, new simulation. Let's think. How are we going to do this? So let's start with... We want to start with a small moon. They excrete whatever excreting. Actually, no, screw it. So let's automatic mass, do that. That's not automatic mass. That's like gonna create too much. Let's do to 3. Oh, whoops. Let's actually look at the kilograms. That's to the power 20. Okay, this should work. Okay, let's get the graphs. Let's roll out the graphs. Okay, radius should come second. There we go. Let's get density. So, start pumping this stuff in. Objects per second, more. There we go. Oh, we got the density and not the average temperature, which average temperature will decrease until we start hitting a critical point due to no star and stuff like that. Actually change this from 13 to 20. Oh, whoops. Okay, so that happened. So this is going to be huge in the timeline. Let's actually just pretend that was all part of the plan and not me just goofing up. So as we add more hydrogen to this thing, it will get more massive, but more importantly, the radius will actually stop expanding at some point, and as it gets more massive, it'll start to get more dense, and as it packs more density within it, and it'll start to heat up, but that heating will not come from quite some time. Times 10 this. Okay, yeah, this is fine. Like this, the star formation is so much mass just being compiled together that, because that fusion starts to happen. The nucleuses of atoms try to repel each other because they're always positively charged. In the plasma, electrons are stripped away, and nuclei and electrons are separate from each other. But since the nucleus of an atom, the smallest unit, the smallest things that known to mankind, since they are positively charged due to protons being positive and then neutrons are neutral, they, in the unfortunate circumstance of being too compressed together that they actually touch, that's what makes fusion possible. And we're actually trying to figure out a way, so let's actually have this level out. Okay, here we go. Let's times 2. We should see a turnaround of the temperature though. Keyword on should. This process takes, I believe, I don't know, so sorry for any misinformation, but it will take an unbelievable amount of time to do anyways. But like millions to even billions of years. Just to complete this process. Now all that mass I was shooting at this thing, okay, no it did not. Here we go. Now what we should see is, okay, if we times 2 it again. This thing is, so let's actually judge this by Jupiter for our graph. So it makes things a lot easier on us. That temperature can do whatever it wants. Let's judge by Jupiter. Now we are actually 1 Jupiter in radius, but we haven't even gotten to the mass of Jupiter. The density is actually going super far down, and that's somewhat of a problem. Probably because, A, we're probably throwing way too much mass at this thing, but the density, if it's way too little in density, it will not form a star. And that is actually a problem. Oh no, we actually hit a point where the radius is going down. So it's times 2. The mass is going up. Like, look at the mass graph. It's going up, but while that's happening, the radius is shrinking. So the density is increasing by a lot due to this. Let's actually go over here. Now density is rebound. Now the radius is rebounding back up. The radius will continue to rebound up. Pile more and more hydrogen into this thing. Let's make it like this much hydrogen. Yeah, here we go. Now the mass is going up massively. And so does the density, but so does the radius. But look at the density. It's trying to stabilize itself. It's fluctuating a lot as we add more mass. It's trying to figure out the equilibrium point of where everything is coming from. And it can't. Let's times 2 it again. So we're at 1 Earth. Alright, here we go. We have hit a point in mass at 13.9 Jupiters, of all places, that it has started fusing at its core. Now, let's continue time along. More mass is being thrown at it. It is slowly becoming a star. Now the temperature is fluctuating heavily. But now the radius, the density is the main issue of this entire equation, because it does not want to follow along. It's not able to attain enough density within its core to actually start fusion. Like, if we go into simulation, view, habitable, like, technically there's a habitable zone for this thing, but it doesn't want to show. Because it's not a star yet, it's still a rogue object. If you look at the temperature, you see like these massive spikes. Those spikes is where it almost actually attains stardom. But the fusion quickly fizzles out. I could try it again. We're reaching 80 Jupiters, and now it's 79 Jupiters. The star is actually a pretty chill star. So let's add. Now, because the solar flares and everything, it's a new star. Now, let's add. So this is where Earth would be if the star replaced the sun. It'd be roughly around here. 1 AU. Far too cold to sustain life. Now, for example, it's so far away that Earth will actually just reach absolute zero. Like, Earth will just freeze over. Not a good place to live. Now, the reason why the star is emitting so many solar flares is that it's a relatively new star, comparatively speaking. Like, it literally just became a star within the simulation within 24 years. How low can you get this? There we go. So with it being relatively new star, let's actually see. Let's actually see. Let's put Mercury in orbit. Now, I don't know what scale this would be on. Mercury finds itself heating up rather quickly, because it is relatively close to the star, and because of how close this is, the orbital period should be slowing down. Because the star is trying to wait, no, it should be going up. Wait, no, I'm looking at the wrong thing. Rotational period. I don't know why the orbital period's fluctuating so much. Is it because the thing is pulling on the star a bit? Oh, it is pulling on it. So if we just, not auto orbit, just zero velocity. Okay, sorry about that. I accidentally broke it. Oops. What happens if we put Mercury where it can get hit with these solar flares? I think Mercury might. Yeah, Mercury's actually just vaporizing away. So, I do have a question. Can you add an asteroid belt to this thing? Oh, due to limitations of the entire game, this is actually pretty interesting. Now, let's open a new simulation, not click on that thing again. Saturn in all of its glory. Let's add Saturn. Let's add its rings to Saturn. Let's add clouds to Saturn. So now its rings are perfect. Okay. I don't know what. We'll experiment that. Then let's go into Saturn itself and let's add the moons of Saturn's moon system. Here is their orbits, and it is a huge chaos. This moon is actually going retrograde, right? Speed up time a bit. Why, yes, it is. It is going retrograde to Saturn. Because Saturn, most of Saturn's moons are just captured asteroids. And actually some of them, like, because of all these particles, they were able to form moons of their own. Titan. The most interesting of all Saturn's moons. I only know two of Saturn's moons, Titan and there's Enceladus, like right here. And Enceladus is what, mostly made of ice? Oh, Enceladus is made of ice. Let me open existing simulation real quick. Just the planets. Just the planets of the solar system. Let's go down. Let's start with Neptune. Let's add Neptune's ring to it. Neptune doesn't have a ring in this game. Okay, let's add Neptune's moons. Most famous of it being Triton. Me turn on orbits. Click on Neptune. Let's slow this down. Now, Triton, you may notice something weird about Triton. And that is A. Like, letter A. Now, of course, other than these moons way out here, Triton has a very weird, like, orbit that is off kilter. It's obliquity, I think. It is let's actually look and see if we can find it. Inclination, that's what it is. Its inclination is hugely, like, different than any other of the moons. So, like, for example, let's go into one of these inner moons, Nead. Its inclination is 33 degrees, as Triton's inclination is around 130 degrees. So it has a truly inclined orbit, and not only that, it orbits retrograde. Now, Triton's future is actually terrible. Saturn is slowing this moon down slowly. Ooh, let's see what happens if we can slow the moon down enough. It's like Kerbal Space Program. Let's see. It's very like Kerbal Space Program. Okay, let's open a different one so we can get a fresh start for Uranus. Now, Uranus, how do I even start explaining this oddball of a planet? Okay, so it's ring. I hope this helps you help me explain it. It's on its side, and then its moons. It follows the same principle of being on the side. Of course, other than these moons which Uranus captured, but like these ones. Now, I have no idea, like, how to even start explaining it, other than during Uranus's early phase, it was slammed with an object that caused it to rotate on its side. But I have no idea how to explain how that affects its ring, how it affects its moons. And there's a moon of Miranda, most famous of Uranus's, I believe. Either that or Ariel, like some of the moons that are named in its ring. Maybe even Marguerite, I don't know. Ferdinand. But this thing is such an oddball when it comes to the entirety of the ice giants. Well, even to the solar system, it's just an oddball. Like, it's on its side, and it's affected the orbits of like its moons. Now, Uranus is an ice giant because it's mostly made of water, which is completely solidified. So yeah, there's that. Uranus has expelled gas from itself. What? I don't Unfortunate to its namesake, Uranus has expelled gas from itself. I don't get it. Oh! Oh, that was a good idea. Okay, so after the educational section, let's break the game over. Saturn, we already tested with that. Jupiter. Okay, Jupiter. So, here's Jupiter's system of moons. It has a couple moons. Oh, I forgot its ring. Was the moon bigger than Mercury? Yeah, there's that too. Saturn also has a moon bigger than Mercury. So let's go with Ganymede, the largest of the Galilean moons, which are the first 4 moons discovered by a guy named Galileo with a telescope that disproved the Earth being the center of the universe. Many people thought the Earth was the center of the universe and everything orbited Earth, but with the discovery of Ganymede, Io, Callisto, and Europa, not in order at all, it's just the names I remembered in order, he disproved everyone about it, and now we know it's not the center of the universe. Now, if we go over to planets, like he said, Ganymede is larger than Mars. Not Mars, Mercury. Mars is slightly bigger, but Mercury can snugly fit inside of it. Now, maybe in mass-wise it's not. Let's actually look. Yeah, mass-wise, Mercury is more massive, but that's probably due to, like, Ganymede probably having, like, more silicate in it than iron. Yeah, far more silicate. I think it's close, but I think Titan is just smaller. No, Titan is bigger. I'm pretty sure Titan is bigger. Yeah, Titan is also... It's roughly the same size, but Titan's bigger than Mercury. Poor Mercury. It's smaller than some of the moons, and that was an honest argument for a lot of people for some people to demote Pluto into a dwarf planet. That it was smaller than a lot of the moons. Problem being, Mercury is still a planet, despite being smaller than some moons. Now, there's other factors. For example, like when Eris was discovered, that's like when it was really finalized. Stuff like that. But like another thing about it was when Ceres was discovered within this large space where the asteroid belt is between Mars and Jupiter, it was labeled a planet. Then Vesta, then other asteroids. But they were more similar to each other than they are to either side. But the problem being with that argument is that these 4 planets, composition-wise, similar, except for Earth. Like, Earth does have a bit of water. And then these 2 planets, Jupiter and Saturn, are similar. And then these 2 are similar to each other. And then you have the Kuiper Belt and then the Oort cloud. So you have the terrestrial planet, asteroid belt. Yes, that is the most hilarious thing ever, though. Russia is larger than Pluto surface area-wise, not mass-wise. I don't know if you account... Oh, no. Americans are larger, probably mass-wise, than Pluto. You never know. But Ganymede, largest moon in the solar system. God, that music got loud. Europa. We're actually looking at Europa. I'm actually gonna put an empty simulation. Have four objects that I do know 100% for certain that we are looking that have a possibility for life. Like, in my opinion, I believe these 4 other planets and moons have possibility for life. Europa is actually one of them, and here is why. It is made of ice. Like, the surface is made of ice. And look at how large this iron accommodates for it. Now, no magnetosphere. It says 0% life likelihood, but that's only on the surface for this game. Underneath this ice here, there could be life due to the heat from the core and the mantle of the moon, the heating of everything. If we can get this, if I probably put this closer to the sun and like sun's habitable zone, this thing probably could harbor some life. I do believe that, like harbor liquid water. I mean, Io. So unfortunate thing about Io, it is ugly. Yes. Quite deep ocean, very deep ocean. Like, I don't think, if we look at surface, it will show liquid water depth. It will allow us, because I don't think to the game there is liquid water. Yeah, no liquid water depth data for Europa. That's also because we don't know anything about it. Here's an aerial view. Yeah, cool. Okay, back to surface temperature. And put that away, and then let's go back to Io. Overview. So, Io. Volcanic sulfuric mess. Yes. But something unfortunate for Io is that whenever Io is about here in its orbit, Europa somewhat messes with its orbit and kind of tugs on it a little. That's what helps with the volcanic things, because Jupiter being the host planet, the host thing, is trying to force it back into its place. And then Callisto. It's just your average moon. There's really nothing like to talk about. It's larger than our own moon, but that's really it. There's really nothing special about it. Now, before we destroy solar systems, I forgot about Mars. I forgot to talk about Mars's moons. No, I just want to open all solar system. Okay, whatever. We can be here. I'm rocking 45 FPS here. I don't know if you guys can see the FPS. I don't know if that's on your end or not. Mars. Okay, let's slow the thing down. Speedy Gonzales, motherfuckers. Mars's moons are... This is not what this thing looks like. No, it is... Okay, Mars's moons are... asteroids. Captured asteroids. They're not round at all. If I look up Phobos, it is not round at all. Nowhere near round. Why we should land on Mars's moons before we land on Mars? It would be much easier to land on Mars, though. If you're already orbiting Mars, why not land on Mars? Yeah, it's split shaped. Same thing with Deimos. I'm hoping they have that correct too. They do not. Okay, that's where simulation. That's where mistake number one is. These two moons are incorrectly shaped, but these two moons also are tiny. They are captured asteroids from the asteroid belt. And the fates of these moons, Phobos would, now either the Roche limit will kick in, tear this moon to shreds, giving Mars a beautiful ring, or it will collide into Mars. Deimos' fate is it's slipping away from Mars and it will escape Mars's orbit. Now this will of course happen like millions of years down the line. Now, let me get the 4 places I believe life that can harbor life. And I will give my reasoning for each of them. Now I'm purposely putting them far away. We're going into chart for this. This way like gravity does not mess with them. Okay. Now, you may be wondering why I got the ones I do. So let's start with the smallest one. Europa. I believe Europa can harbor life because, yeah, same with our own moon. Our own moon is destined to actually escape Earth. So there will come a time during humanity's life on here, if and only if we can save the planet from global warming, that humans will no longer be able to experience a full solar eclipse. And that'll be a sad day for humanity. But back to these 4 objects I placed here. Europa. I believe Europa can harbor life underneath the massive ice sheet it has. Do we even know how thick this ice sheet is? That is a very good question. How thick is this thing? So it is on the scale of Earth. It is 444 kilometers thick. The ice sheet is. Okay. Like, it's a quarter of the diameter of the moon. That's how thick the ice is there. So, because of that, the water that's any liquid water that is underneath this ice sheet, any like giant ocean, will actually be heated enough that chemical reactions for energy and to move around will actually be feasible. And we will never know what's underneath this thing. There could actually be advanced civilization underneath this that is trying to escape the ice, but we will never know. Never. Until we actually land here. And then dig into this massive amount of ice. Titan. Well, the first and only thing you see on Titan is the atmosphere. Mostly made of methane and carbon dioxide, as well as other carbonates and nitrates. Yes, so basically Atlantis. Like, Atlantis can be under Europa. Now, we don't know if it's inaccuracies between the recordings of the atmospheric composition, or if there's actually life on this planet underneath this atmosphere that is altering the atmosphere. We have actually formulated a cell that does not require water to live at all, because water is, like, liquid water is non-existent. It's liquid methane. Which there's really no term for liquid methane. I have an idea. I have a really good idea. I'm actually going to use what scientists use. I'm actually going to do an English to Latin translation of liquid methane. Hang on. Liquid methane. Let me... Okay, so there's really no translation. Got it. So, liquid methane. Let me think. Liquid methanol, or just methane. So there could be like methane lakes down here due to the extreme, not really extreme, due to the atmospheric mass, creating a heavy surface pressure of 987 millibar. That is actually around, if we were to take this and put it on Earth and put it in like the tropics, this would be like a really like a powerful Cat 2 to like Cat 4 hurricane in like the Atlantic Ocean. Like, not really the Cat 4, but like Cat 2, Cat 3, somewhere in there. Like, it could be a good hurricane. No, like, it's just a hurricane in general. So that hits methane's tripper point, so it can exist as a gas, solid, and liquid. Same thing with this temperature. Now, if we look here, like, water's boiling and freezing point, doesn't make a difference. This makes 0 difference. Doesn't do anything. So, That's all for Titan. Mars. So, we know from, we actually do know that Mars used to host oceans on its planet. And they were concentrated in the northern side of it. I'm trying to find the crater, hang on. So if all that's there, the crater should be like down here somewhere. Obviously nowhere near Jupiter's red dot. So Mars actually did used to harbor liquid water on it back when it had a magnetosphere and a more dense atmosphere. But because of how small Mars is, its iron core cooled too quickly. Like it doesn't have a large enough of iron core to sustain a magnetosphere. So based off of that, the magnetosphere died with that, and so it was now left open to the endless bombardment of the solar wind from the sun, which killed off the planet. And all of the water retreated away, either as part of like there is ice on it. There like in the northern and southern hemispheres. Oh whoa, what the hell? But it's not. But that's not where it mostly is. It's mostly permafrost. Now we have observed some flowing water still. It's just barely flowing though. It's not to the extreme amounts as like a creek or something like that. That's like barely any water. But life could have actually retreated to underneath the soil. Like we know soil, like especially mud, to be very life rich. And that is where life actually harbored itself first on land, from mud. Now under the water and everything from volcanic vents and everything. But like we are actually planning on sending humans to this planet, and maybe like those humans will be the first colonizable people. I guess the mole people of Mars. That could very well be possible. That can very well be possible. We just need to get underneath the surface. Now, my last one, Venus. Now, this is the most stretched one as I can get it. So, Venus. I believe the atmosphere is mostly made of sulfur dioxide. Hold on. The Venetian atmosphere. Carbon dioxide. Okay. Sulfuric acid. Okay, I thought it was sulfur dioxide. Sorry guys. So the Venusian atmosphere is mostly made up of carbon dioxide, which life can use to create other things, but one of the main inhibiting factors is this average temperature of 922 degrees Celsius, which, for those that don't use Celsius, 791 degrees Fahrenheit. But I use Celsius. So the unfortunate thing about that is it's really difficult for life to exist, but not only that, it's the extreme pressure found on Venus. The average pressure is 92,516 millibar. There is more pressure than there is in 91 atmospheres worth of pressure, which is insane. The density of this atmosphere is also like crazy insane. Like there is barely any way life can actually harbor itself here, but I do believe like there are animals there are certain specimens of life, like a very famous one, that are known as extremophiles, a very famous one, known like the tardigrade, known as a water bear. We sent a group of tardigrades up to space and let them in the vacuum of space, the literal vacuum of space. Like, I believe 80% of them was still alive. Let me actually look this up, because looking it up always helps. These things also, whenever water, yes, and it's the hottest planet due to this atmosphere that traps in the heat. It's a huge greenhouse effect, and because of that, it's heating up the mantle and its core as well. Due to that, and because of them heating up as well, it's expanding the planet slightly, and the crust is starting to break open, and within millions of years, the crust will finally break open. I think even thousands of years, like hundreds of thousands, the crust will finally rip itself open, and then lava is flowing everywhere. It will be a sweet release of pressure, but he will superheat the planet again. So this planet is destined to be just hot forever until the sun swallows it. Which, hold on, I forgot a fifth object I believe life can live in. Hang on. Um, Hold on, let me find it real quick. I believe life can live in Sagittarius A star. I'm just kidding on that one. That is not possible. I don't like. I don't think it's possible for life to live inside of a black hole, but might be. Might be possible. We just don't know. Look how strong the black hole is. Like, oh, you caught the. Can you? You caught the charger. Hang on. Oh no, it's really wrapped around there. This is why you don't really spin when I'm charging this, okay? Sorry about that. Are these things that go towards Sagittarius A star? Oh no, it's speeding up fast. Okay. What happened to it? Why is there a red spot? Oh, did it collide with something? The white hole. Now, this is where this is something I am really not that familiar with. So, I'm gonna do some research real quick. Let's look at. Okay, let me show you guys this real quick. Nope, this is not what I wanted. Okay. Yeah, hang on. We will be doing some research real quick. Hang on. Okay, so here's my display and everything. So white hole, hypothetical region of space-time singularity that cannot be entered from the outside, although energy, matter, light, and information can escape from it. Okay, reverse of a black hole. Okay, so that's what it is. So it's just a literal reverse of a black hole, which can be entered only from the outside. And so I'm actually thinking now. I'm starting to think now, based on this information, that a black hole is actually just a wormhole, and the other side of the wormhole is a white hole, and it spews stuff into this alternate dimension, into an alternate universe. Yes. So like the black hole sucks things in and then throws it out a white hole in a different universe. That's exactly what I'm reading here. That is a theory that I formed up just from this. So it's insane. So I mean, I can probably just hide the game capture and like I don't know if you guys see it. Can you see the game? Oh, you can. Oh, interesting. But I would rather the game capture instead. What in the world? Okay. Let's add stuff to this thing. Pinwheel. Let's actually put these. Let's put these galaxies in a fight contest. Did I add pinwheel? It looks like no. Wow, my game is running real slow now. Okay, so let's see how this thing goes. We really need speed up time because we're dealing with galaxies here. Okay, let's turn off the trails. Now, we obviously should know what the winner of this is. You know? We should be able to figure this out. Okay. Oh. There you go, Sagittarius A star. Which is the supermassive black hole within our Milky Way galaxy. Hi, Chocolate. We're learning about space. So, in this galactic fight, we should know who's going to win due to its black hole and everything. But not only is it a black hole that is keeping that galaxy together, it is dark matter. So now the Milky Way is going to have a brawl with this galaxy. Okay, let's actually go into... Let's go look at... let's do this one again. Milky Way and Andromeda colliding. So, 4 billion years from now... these two galaxies will collide. Oh, that is nice, Choco. I should do a chess stream at one point. That would be interesting. This collision will result, mutual gravitational attraction of stars, planets, and other matter, and they will produce a single galaxy. So, let's watch this happen. So, Andromeda is a lot bigger than our Milky Way, but our Milky Way has 4 spirals. Andromeda has 2. There's also... There we go. Now the galaxies are really starting. So, the black holes are just going to instantly merge. So now a lot of the nebulae are going to fling out double queens. Oh Jesus, that is terrifying. Hey Choco, after the stream in like 5 minutes, because I don't really like I will be in the stream real shortly. Wanna play some chess? Like I'm thinking of setting up Thursday as an educational stream idea, and then like the rest of the time, whatever the hell I want. Whoa, whoa, whoa. What's this? Guys, you see this? Oh, it's just, thing. Well, we'll see about that. So, let's continue forward with time. So, the Milky Way galaxy. You lost a lot of rating? Jesus. Did you at least watch the videos of, like, the beginners of chess and then, like, some educational chess stuff from that other guy? From Gotham? Okay, so at least you learned something. So I won't be playing anything fancy like the Sicilian or anything against you. I'll just be playing E4, E5, D4, D5. So like you at least get some sort of fundamental basic. I'm not gonna play anything fancy like, I might play the French defense, but it's just more of a slow moving thing. And I'm trapping my own light squared bishop in because I commit so many pawns to light squares. You know, so. Milky Way and Andromeda colliding. It produces a not so beautiful galaxy. So for example, the Milky Way looks majestic the way it is. Now, this galaxy is now a lot larger in size due to the gravitational. Oh, you want me to stream the chess? You really want me to stream me destroying you at chess? I didn't think about that part, but sure. Alright. So, I will be actually ending the stream soon, though. So, the Milky Way and Andromeda, a huge collision course. Now, it will be much different than that because of the way everything is working between them. They are gravitationally somewhat pulling each other toward each other. So, they will collide, and the way it'll work is their black holes will actually orbit and get closer and closer until they collide themselves. I believe Sagittarius A star 1. Yeah. So Sagittarius A star. Actually, I actually want to look at something real quick. Because Sagittarius A star 1, but Andromeda Galaxy is much larger than the Milky Way. Like quite a bit. It's 2 Milky Ways in diameter, but has half the mass of the Milky Way. Wait, what? So the Andromeda black hole has 2.1 million suns. Okay, what about Sagittarius A star? Has what seems to be 4.3 million. Okay, so that's why Sagittarius A star won. It's much more massive. So last thing before we end the stream, and this was actually a request by someone, is to replace the sun with UI Scuti, the largest star that we know. I believe it was actually surpassed by another star. Oh, oops. Stevenson 218 or something like that. It's named Stevenson. Replace object with star. Let's look through UI Scuti. Here's how big UI Scooty is. Now, if we turn on the habitable zone, look how large this habitable zone is. Like, the UI Scooty goes out to Saturn's orbit. And Saturn is a burning ball of gas. Many explosion spots are forming on UI Scooty right now because it, like, ate everything in the inner solar system. But because the mass of it, it's gonna draw everything in and probably gobble some of it up. But it is so bright that Sedna, at one point in time, will be habitable. Actually, Sedna is no longer habitable. But Sedna's orbit with the sun, it can actually reach habitability temperatures. Not habitability with anything else, but just in temperature. So let's add the Earth. Add the Earth there. Let's try to get habitable Earth. This Earth is not gonna work out. Okay, so we need to get closer to the red. What about there? No, this one's not gonna work out either. What about here? And now it's heating too much. Will it actually level out? Actually, no. UI Scooty is... The hell is happening? That's the average temperature. Alright, what's happening here? Ah, that's what's happening. So, okay, this is completely fine. I don't really care. So, the Earth, let's just say it's habitable. No, the UI Scooty is from our, galaxy. So, to make Earth habitable, we kinda had to put it far away, and that results into an orbital period of 6,000 years. 6,000 years ago, like we were starting to figure out farming. Like 6,000 years ago. That massive increase in time. Oh, we replaced the sun with the UA Scooty. We saw black holes collide. Well, solar systems merged. We saw the everything about the planets with moons and stuff like that. Educate y'all about some of the moons. We formed a star out of just hydrogen and from a random moon we picked just from random. Yeah, I believe that this was a very successful stream. Yeah, a black hole. I'm thinking of talking about Messier or something like that, the first photo of black hole, but I will see all you guys next time. If you guys actually enjoyed the video, or the stream, and, well, video too, I'll see you guys tomorrow. Peace.